Computer transistors, computer growth. This is that stereotype where people say if you buy a computer today, it'll be outdated tomorrow. But here's kind of an example on how this exponential growth or uh, a nonlinear growth at least would look like. When I was in college, the very first flash drive I ever purchased was a 125 kilobyte flash drive, and that was the biggest one that they made. Shortly thereafter, they made a 250 kilobyte flash drive. Eventually, you could buy a 1 megabyte flash drive. Well, now, for a little bit of money, you can buy a 4 gigabyte flash drive. This type of data, and the same thing with your hard drives on your computers, they keep doubling and doubling and doubling. So in this particular case, if we look at years since 1970, so in other words, this isn't 1910, this would be 1980 because it's 10 years since 1970. There's a little bit of growth and all of a sudden a shoot up of the transistors used in computers, transistors being sold. So this is like an exponential growth model here. There are certain properties that we need to make sure we're familiar with logarithms. They're listed here. So for the purposes of this course, we're going to use log base 10 or the natural log. So log base 10 or the natural log. Now log base 10 is just convenient to use in this class because we're not getting into more complicated levels. So as we look, we got a couple different things. Log of two numbers multiplied is the same thing as adding the two numbers after they've been logged individually. So in other words, in this particular case, multiplication and addition pair. We have division, so we subtract. We have exponent, so we multiply what's out front. So on that previous example, years since 1970, transistor total, clearly exponential graph, applying some of our our logarithms, we linearize our data. In this particular case, they're using the natural log. We'll get into some detail in class as to when you would use a natural log and when you wouldn't. So if we put a least squares regression line on our graph, we've got a nice solid line that we can work with. So we make a residual, and again, our residual be cautious about because we want to make sure we use the proper explanatory variable. Now in this case, our explanatory variable doesn't change because we took the natural log of our response. So we don't need to do anything other than use that actual data. Now, a little caution because it appears as if there's a little bit of a pattern that in the early stages we underestimate, the middle stages we overestimate, and then we start underestimating again. But we have 5 things on top, 6 on the bottom, so they're still somewhat balanced. And when we look at these numbers here, these are small numbers, so it's not like they're huge distances. So this a residual says we kind of have an okay line. And if we were to log the bacteria example, that would be virtually a perfect line.